Yeah, unfortunately, I can't see you. That's really strange, but I hope you're all there. So yeah, my talk today is based on joint work together with my supervisor, Roland Langrock, and Ruth King, and the biologist, Nicola Quick. So, sorry. Actually, our project, it started as an applied project where the aim was to analyze the annual movement patterns of bottlenose dolphins along the east coast of Scotland. So when you have a look at the map here, these black dots, they indicate places where dolphins have been sighted. And as you can see here, we have two main areas actually. So the first one is the one up here north. That's the special area of conservation, including Outer Moray Firth, which for simplicity, I will just refer to as SAC. The second area here is Tayside and Fife, which in short, I will just call TNF. And the dolphins, they are known to move between these two main areas. Now, the problem is that there's also ongoing offshore development on the Scottish East Coast, and this potentially disturbs the dolphin population. So therefore, it's important to gain a better understanding of the movement patterns of the dolphins, to inform decisions and to also minimize any negative impact on the dolphin population. Okay, so the data we used for our analysis were collected via so-called photo identification trips. On those trips, people go out on boats and take photos of the dorsal fins of the dolphins. So down here you can see two such examples now. And then afterwards, the dolphins are identified based on long-lasting natural marks. The dolphin population on the Scottish East Coast has already been studied now for more than 3 decades, resulting in more than 1,000 boat trips over the years. In our analysis, we included more than 370 dolphins, which have been observed for at least 6 times over the years, so resulting in a median sighting number of 27 overall dolphins. Okay, so the information in that data set we then summarized in so-called capture histories. So here you can see such an example. And with 1, we denote that the dolphin has been seen in SAC, whereas with 2, we denote that the dolphin has been seen in TNF. However, as you can see here, at most of the capture occasions, the dolphin is not observed at all, which we then denote by a 0, resulting in this particular capture history here in the example. Now, the challenge in the data set is that our capture occasions, they did not follow a regular sampling protocol. Sometimes there were just a few days between capture occasions, and sometimes we had weeks in between. And the problem is that standard capture-recapture methods are not readily applicable to such a data set. And therefore, we developed our new method, which is suited for irregularly spaced capture occasions. So the main idea of our method is to regard the capture histories as a realization of a partially hidden Markov model. Up here, we've got the so-called state-dependent process, which corresponds to the observed capture histories of the dolphins. And underlying that one, we've got the so-called state process, which here corresponds to the actual location of the dolphins. And that is, of course, partially observed, because when we see the dolphin in either SAC or in TNF, then of course we know its location, it's in SAC or in TNF. Only at those capture occasions where we have not observed the dolphin, we cannot know its state. And in particular, if we haven't observed the dolphin for quite a while, it might also be dead. It's also possible. Also to mention is that due to the irregularity of our capture occasions, our state process is modeled using a continuous time Markov chain here. So focusing on the state process, where T denotes our capture times. As I already mentioned, we have 3 states. That is, the dolphin can either be in SAC or in TNF, or it might be dead. We're calling this 3rd state presumed death because we don't have any information on whether the dolphin really died or if it just left the study area. As we're in continuous time, our state process is governed by a transition intensity matrix Q, and the elements of this matrix, those QJKs, can be interpreted as the rates at which transitions from state J to state K occur. Here, our third row only consists of zeros. That is because we assume that our third state, that's the presumed death state, is an absorbing state from which no transitions back to the other states are possible. Okay, now the good thing is that as long as the transition intensities do not depend on time, we can use this nice closed form expression down here to calculate the transition probability matrix gamma for a given time interval. And that is the matrix exponential of Q times the length of our interval. And so gamma then contains the probabilities of switching between the states over the given time interval. Okay, coming back to the state-dependent process, as I said, the events that can occur during capture occasions is that we either do not observe the dolphin or we see it in SEC or in TNF. What we also now need are the probabilities of these observed events. And this down here might look a bit confusing, but it's actually not, because all we're doing is we just differentiate between the different scenarios that can occur. So what are these scenarios? First of all, we might go on a boat trip in SEC. The dolphin is there and we observe it. This happens with probability P1. That's the so-called detection probability. Then we might again go on a boat trip in SEC and the dolphin's there, but this time we don't observe it. This then happens with probability 1 minus our detection probability. And it might also be the case that we don't go on a boat trip to SEC, but the dolphin's there, but since we're not there, we cannot observe it, which thus happens with probability 1. Then we've got the same here for TNF, only that TNF has a different detection probability. Finally, it might be that the dolphin's dead, so we cannot observe it, which again happens with probability 1. Okay, so there's a great advantage of formulating our model within an HMM framework, and that is that we can use the HMM-based forward algorithm for parameter estimation. So here we've got the likelihood written as a matrix product and conditioned on the first capture of the dolphin. Here pi is the initial state vector and the P matrix is a diagonal matrix, which in fact just contains the information from the previous slide. So we then estimate our parameters of interest. So those are the transition intensities and the detection probabilities by numerically maximizing the joint likelihood then over all individuals. But again, it is important to mention that this expression here only holds as long as our transition intensities do not depend on time. However, as I mentioned in the beginning, we were mainly interested in the temporal movement patterns of the dolphins. So what we'd like to do is we'd like to model the transition intensities as a function of the time of year. Here using the sine and cosine function and exponentiating the linear predictor because the intensities need to be positive. Now the problem with this equation is that it renders the likelihood calculation intractable because as you can see now, our transition intensities do depend on time and thus this nice closed form expression I showed earlier doesn't hold anymore. Well, as you can already see down here, there's an important exception, and that is the case when our transition intensities are piecewise constant over time. To achieve this, we divide the interval in which we have made all observations into capital R intervals, where CR is the center of each interval. And when you now compare these two equations, all we actually do is we replace our continuously varying time t with these CRs, such that our transition intensities are then constant on the intervals. Why do we do that? Well, by using these piecewise constant functions, we can avoid the integrals, which otherwise would occur in the likelihood formulation. So again, now we can use the same likelihood evaluation as before. The only difference now is that in order to calculate our TPM gamma, we have to take into account all interval breakpoints, which might occur between consecutive capture occasions. So this is best explained when having a look down here. So when we want to calculate the probability over this long interval here, what we do is we calculate it recursively over those shorter intervals, because on these shorter intervals, our transition intensities are constant. So again, we can use the closed form expression, which I already explained. Okay, now coming to the main results regarding our bottlenose dolphin data, and that is that you can see a clear yearly pattern. So in summer, the dolphins have higher intensities to move up north to SEC, whereas in autumn they have higher intensities than to move back south to TNF. And finally, just a short discussion. There's one main point I'd like to highlight, and that is the choice of the time formulation in modeling. So the way I see it is that continuous time models are clearly conceptually appealing because, well, animals in general, they just move in continuous time. And in addition, continuous time models are also more generally applicable as they can accommodate different temporal scales and in particular irregular sampling as in our case here. But on the downside, continuous time models are also technically more challenging. Yeah. So these are my references, and if you're interested, there's also a preprint available on arXiv. Thanks for listening, and I'm happy to hear your questions.